Last time we talked about addition, didn't we? Was it addition last time?
We did some work. I kind of slowly snuck in the fact that my made up CPU was in fact a real CPU, the one that I grew up with, and I showed how we could use it to do addition of multiple values to show that arbitrarily big numbers could be added up by this relatively simple system. What I'd like to show today is how CPUs have sort of advanced a little bit beyond that very simplistic view, and this is one of the reasons why they're so fast these days. And I think there's going to be a whole number of like little technologies that each of which feeds into the next, and if I explain one without the others, you'd be like, why on earth would it need to do that kind of thing? So we're going to start at like the basics. So where we start is, if you remember our story so far, we have a little robot in my mind that sits inside the computer and does all of the work. And the work is relatively straightforward pieces like read a number from memory, add it to another number, store it back into memory, compare numbers, those kinds of things. And the way that we realized that we could explain to the robot what it needs to do is that we could write down numbers that correspond to the kinds of things that it might want to do. So like 1 might be add, 2 might be subtract, 3 might be multiply, those kinds of things. And then those very numbers themselves can be put into the memory alongside the data you're manipulating. Mm-hmm. The robot's kind of job is, we've got our pigeonholes that are the memory, and we've got like number 1 over here, which means add. So the robot goes, first of all, looks up, what am I supposed to do this step of the recipe? 1. Looks up in his big chart and says, oh, 1 means add. Okay, so now I need to do some adding together. And then he goes over to his abacus and he does the addition or whatever, and then he's got the result back, and he looks in the next slot and it says, 2 is store. And he goes, okay, well, then I guess I should take that number and I should put it somewhere else in the pigeonholes. And that's how our whole computer program works. Now, so there's kind of 3 steps that the robot goes through for every single step of the recipe. The first thing is he has to go and look up what is the next step in the recipe, read out the number or numbers from the memory cells that correspond to the instruction that he's going to be doing. Then he has to make sense of them in somehow. Maybe he has to look up in his chart that 1 means add and 2 means whatever. And maybe also if it says add, he has to go and get another number, which is like, well, what is the number I'm going to be adding to? Right? And then in the third step, he actually does the addition. He executes. I don't know why he's a he. I was actually thinking about this. I was thinking, should the robot be maybe non-binary? But then it seems really ironic to call a binary robot non-binary. But so like anyway, he, she, the robot, it, let's be it, goes and does the actual work with the abacus. And if you can imagine on the circuit that actually corresponds to the robot's mind, those parts of the chip are very separate. The bit that goes out to memory and pulls numbers out of memory, the bit that has a big table that says this is what this means, and the bit that has all the abacus parts, as it were, which is actually, we call the ALU, the arithmetic and logic unit. Those are very separate parts of the chip, which means that each phase, there's a whole part of the chip that's not being used, and that seems incredibly wasteful. There's only so much we can do in every tick of the clock. So behind the scenes, there's a sort of like a metronome going on that says, now it's time to do the next piece of work. And, modern computers, that metronome runs at gigahertz. Back in the day that I'm talking about here, we're talking about megahertz, thousands of times a second. But it still means that each of those steps is one tick of the clock. So fetch, decode, is work out what it is, and then execute, and then fetch the next thing, decode, execute. Most of those steps don't overlap with each other. So one of the classic sort of solutions to a problem where you're going to be doing a sequence of work with repetitive steps is to build a production line, much like, the Model T Ford, where, the first thing you do is you assemble the chassis, and then someone else puts the engine block in, and then someone else puts the wheels on, and then someone else polishes the car, and then the car comes off the end of the railway, the conveyor belt, whatever it is. We're going to do the same thing inside our chip. So the way that I like to think of this is that we're going to break fetching, decoding, and executing into 3 steps along a sort of conveyor belt inside the robot, I guess. And on the far left-hand side, again with the pen that's running out now, here is our robot at this end of the pipeline. Conveyor belt, whatever we're going to call it. There is his little ears. He's got, I think of it like a spade, right? He's actually going to shovel on the bytes from memory. He's just reading the next number from memory, one after another, and he's putting them onto this conveyor belt. Our numbers, 1 and then 30 and then 50. He's just picking them up and putting them onto the conveyor belt one after another with no real thought, no logical thought behind it. Somewhere down the conveyor belt is the decoding robot. And the decoding robot has, in my idea, he's got a sort of magnifying glass which is about the only limit of my drawing here. And he's got the book of all of what do these opcodes mean? What do these numbers actually mean? You know, is this an add, and one means an add, and then the next two numbers mean, well, those are the numbers I'm going to add together. And so he waits until he's got enough information on the pipeline, on the conveyor belt, to be able to decode an entire instruction. And then he writes down a new piece on a card, internal, that just says, you know, like add 10 to address number 57 or whatever. Sorry, that's my too small to see. But that's what he's doing. He's going to add it onto a new piece of card that goes down the conveyor belt to the next person. And the last person on the line in this instance here is our robot who has the abacus. He then picks up the card and says, oh, add 10 to memory location 57, pulls the number out from memory location 57, adds 10 to it with the abacus, taking whatever time it is. And you can imagine that might take longer for like multiplication or division or whatever. And then he'll write it down on one of those, you know, pieces of paper that we've got. We called them registers before. You know, we had like the A register, the X register, whatever, however many registers our CPU has. And we haven't fundamentally changed anything about what was going on. We've just broken what was 3 pieces of work that one robot did into 3 pieces of work that 3 robots do, one after another. Any one instruction takes 3 stages to get through the system. He has to go through the fetching, he has to go through the decoding, and he has to go through the execution. So it still takes 3 metronome clicks before that particular thing has finished. But what you'll notice is that if we can keep it fed, if this robot on the far end can get shovel bytes in fast enough, and this decoding robot can decode fast enough, then every single metronome click, this executing robot is doing useful work. He gets to use the abacus every single tick of the clock. So we're getting much more use out of our CPU than we were before. Previously, the abacus was only being used every 3rd instruction cycle, so it's like wasted. And that means that although any one instruction takes 3 cycles to go through our system, every cycle a new thing rolls off the end of the production line, and that's fantastic, and it makes it go a lot faster. Now there's a sort of catch though, as there always is with these things, right? It seems great. We could stop the video here and be like, oh brilliant, computers go 3 times faster if you break it into 3 bits. But the eagle-eyed among you may have realized that this is all well and good, provided our robot here on the far left-hand side knows what the next thing to do is always. And it's a reasonable guess just to keep reading the next recipe instruction out every single tick of the clock, right? But we know that one of the things that the execute unit can do is to branch, to say, actually, I've made a decision and I'm going to start doing something different now. Like I compared the 2 numbers and actually we're going to go to the top of the loop now. So if I draw out a short version of the program that we had before, it looks something like load from like address 100, say, which this was the Fibonacci program, which I realize now that I was doing wrong, but we're going to stick with what I was doing before. We're going to add the next number. This X is just an offset to say which number of the Fibonacci sequence are we doing, and then we're going to store at 102, X, and then we're going to increment X. And then we're going to compare X to say, have we done 100 of these numbers? Because after 100 I need to stop, for example. And if X was not equal to 100 here, we're going to branch if not equal back to the top of this loop up here. So this means the sequence of bytes. So each of these then corresponds to some number of numbers in the pigeonhole. You know, this may be 1 followed by 100. This may be 2 followed by 101. This may be 3 followed by 102. This may be 7 to increment the X. This may be 8 and then 100 to say compare with the 100, and then 9 and then something that says back to the top of the loop.
So the first number there is the instruction number, and the second one is the
is this number that's part of the the address in this particular instance.
The address of the thing that did in the sequence. Yeah, okay.
Exactly right. Yes, yeah. And there's not an obvious way to tell that just looking at that sequence of numbers 1, 100, 2, 101, which ones are instructions, which ones are data, which ones are numbers, whatever like that. That's partly what our decode robot has to do, is make sense of this stream of numbers and say, well, these 3 things correspond to one instruction. So it's not terribly obvious. You can't just stare at it and go, oh, there's a sequence of numbers, I know exactly what that is. And that process is called, when a human does this, it's called disassembly. You're actually disassembling the code back into the assembly human readable version over here. I say human readable, obviously, you know. It's not that human readable, but it's more human readable than a sequence of numbers.
Quick aside question on that, though. Assembler and assembly, what's the difference between those two?
It's one of those things where I think
Semantics.
colloquially people use it wrongly all the time. So assembly is the name of the text format, and assembler is actually the name of the program that assembles the code. But we somewhat interchangeably use them, and I'm as guilty as the next person for saying assembly when I mean machine code as well, or assembly, assembler and instruction or whatever. It's all a bit vague, but you know the sort of distinction is that the numbers are the machine code. That's the thing the machine understands.
Yeah.
The assembly, or you know, these opcodes is the assembly code that you assemble with the assembler to make machine code. But good question, and a very
I think
commonly.
we're there. Go for it. Go.
Yeah, no, absolutely. So we've got this sequence of numbers, and if we were to just, these would be laid out in memory sequentially, and so we'd be absolutely fine. Our robot who's feeding the front of the pipeline would be fine right up until we get to this branch, where by the time the branch has made it through, there's maybe some other instructions here. What are we going to call this? Well, let's say that the next instruction was return, because it would be the end of the routine, and then there was just any garbage afterwards, actually rubbish afterwards. By the time this branch instruction has made it through the pipeline to the execute, where the executing robot goes, oh, wait a second, we need to go somewhere else now, the pipeline is already filled with the decode robot's already decoded this return, which we don't want to do, and the fetcher has already fetched probably the bytes that correspond to whatever these things are immediately afterwards. And so in the simplest form, which is what most of the original CPUs would do, the execute robot kind of pulls the break time horn, you know, the Flintstones thing, right? Everyone stops, and the pipeline is restarted. Everything is thrown off of the pipeline. Everything is pushed into the trash, into the rubbish. And we start again. So then from that branch from the top of the loop, we start the pipeline up. Now that means that we have to wait 3 cycles before any useful work gets done again, because, you know, we started from scratch. And that's terribly unfortunate. But if we don't branch very often, then it's still a net win to do this. The problem is we do branch quite a lot. It's kind of every 3rd or 4th instruction in most programs is a branch of some sort, and so it's really worth our while trying to keep this pipeline full of useful work rather than discarding it, flushing the pipeline. So there are several approaches to solving this conundrum, and we'll do a couple of them, and then the one that we use nowadays I think is big enough for its own topic. One thing we could do is we could say, how about the next instruction after a branch gets executed anyway, even though it may not be following the path of that branch. If the branch says go somewhere else, we just say, hey, let's do that work anyway. It's already fetched it all the way through the pipeline. We've decoded it. It's about to start executing. What the heck? Let's execute it anyway. Now that means that the programmers have to know that that's happening. We have to write our code specially. So in the particular case of our loop here, I don't even know what you would do in our particular loop here, but you would try and find another piece of useful work that you needed to do anyway, and you would put it immediately after the branch. So you'd say branch if not equal to loop, and then some other useful instruction here. Now, again, in our particular example here, there isn't a useful thing, so we'd actually end up putting a NOP there, don't do anything here on purpose, to say, look, it's better than flushing the pipeline, but don't do anything here. Maybe you could be clever and you could move the load from the top of the loop down into the bottom of the loop and then say, okay, now we'll load the next number ready, and then instead of jumping all the way to the top of the loop, we branch to the second address of the loop. So you can kind of move it around, and this is where things like compilers that write the code on behalf of you, they can do these things for you. This little instruction immediately after a branch that's executed anyway is called a delay slot. And it's a very simplistic way of being able to continue doing useful work even when the pipeline would otherwise be flushed. It just puts the burden on the poor programmer to write their code in a particular way to take advantage of it. So that's one way you can do it. Another way you can do it is, and this is what the folks at ARM decided to do, is that if you take a look at the majority of branches, they, with the exception of these looping ones where we go back to the top, oftentimes you might want to do something along the lines of compare it with 10. If it's greater than 10, then set it to 10, otherwise leave it alone. So that would be like taking the maximum value of something. Your instructions look something like compare x with 10, branch if less than to skip. That is, hey, skip some instruction. I'm going to write skip down here. And then we're going to say load x with 10. So this is clamping my value of x to say the highest number I ever want x to be is 10, whatever it came in as. So I'm going to compare with 10. If it's less than 10, then skip over the next instruction. I just don't want to do that next instruction. And then the rest of my program carries on here. Otherwise, set x to be 10. And that's a very common thing you might want to do, right? Or you might have some other branch which is like, well, if it's not 10, then make it minus 10 or some other thing like this. So most of these branches are just skipping over one or two instructions before they carry on and blend in with the rest of the flow of instructions. So what the clever folks at ARM decided to do, at least with the original ARM processor from like the late 80s, early 90s, is they said, well, what if instead of just this branch instruction, having this sort of like condition, branch if less than, branch if not equal, what if we made every instruction conditional? So in the case of like ARM, and this is where I'm going to show up the fact that I haven't done this for years and years and years, we might do something like compare register 10 with the number 10. And I realise this is a slightly different style. I just want to do this in case people are familiar with ARM. And then what I might do is move if greater than register 10 with number 10. There's no branch anymore now. I've just said do the comparison, and then this move instruction doesn't do anything unless the comparison was greater than. It's essentially a NOP if that's not true. And so now my pipeline doesn't have to be restarted. I just have a bubble of one instruction that either gets executed if I need it to, or it doesn't get executed and just flows throughout the other side of the pipeline. So I still haven't had to re-steer everything. I haven't discarded the instruction after that's work. And so that's a really smart way of, for small sequences of instructions, avoiding having to restart the whole pipeline just by saying, well, skip that one. Okay, now we're good again. So it's kind of similar to the delay slot. You're pushing the burden on the programmer a little bit, but you've given them a tool to be able to do this. And then the last thing is to somehow teach the fetch robot at the front of the pipeline how to be clairvoyant and to look into the future and predict and make some guess as to where the flow of execution is going to go, even though that robot has no other information at all. And then I think that's a whole other topic, because that is how most modern processors work now, and it's called branch prediction. It's a whole very interesting area of exploration, and it's all in aid of trying to keep this pipeline of fetch, decode, and execute filled with useful work that we don't have to throw away. And in modern CPUs, I've described it as 3 steps here, but modern CPUs have hundreds of steps, so it's even more important that you steer the front of the pipeline in the correct direction. Otherwise, you spend most of your time waiting for this pipeline to fill back up again.
I would imagine this kind of fire hose of data, if not the opposite. Redundant data coming out the end.
It is exactly right. And it is a fire hose these days, because another trick that CPUs have up their sleeve is that they can use, maybe they have, what if you had 2 abacuses? Imagine you had 2 of them, right? Now you could actually imagine having 2 of these robots at the end of the pipeline with their abacuses. And if you can fill this pipeline up fast enough, and you can see that there are 2 instructions, one after another, and neither of them refer to each other, so one's adding 10 to the X register, the other one's subtracting 1 from the Y register, why don't I do them at the same time? And my 2 robots at the end of the pipeline can do 2 instructions at the same time. And in order to make that work, I have to fill this pipeline up faster and faster and faster to get enough work to be able to do more than one thing at once. And that's another reason why we have to make sure the pipeline is filled with useful work at all times, and that these complicated thousands of steps or tens of steps that happen. It's so cool. It's so amazing, and most of the time we don't think about it. We don't know about it.
One last question on that then. Is there any issue with accessing the pigeonholes? So I'm thinking you've got a fetcher, you've got someone who's trying to do some adding and storing, and are those things that need to be managed as well?
Absolutely, yes. So there are 2 parts that I sort of glossed over a little bit here. One is that, yes, maybe the pigeonhole, only one robot at a time can access the pigeonhole. And so if the executing robot needs to write back into the pigeonhole while the fetching robot is trying to fetch more things to put into the pigeonhole, then yes, you might be in trouble. And that's solved by giving the solved in two ways. The fetcher can pick up lots of things at once from the pigeonhole. So he goes to the pigeonholes and gets 16 of them in a row.
That's
and kind of
like
goes,
caching,
okay, that
I
gets
suppose,
me.
He caches some of that.
And then, he also can have a cache up here where he's like, well, I keep fetching the same things over and over again. Why don't I just have my own private copy of what's in those pigeonholes, and then I don't have to bother the pigeonholes as much. And similarly, on the executing side, there are caches here. So this is why we typically have an instruction cache separate from a data cache, so that we can have the two robots like not have to fight with each other. So you're absolutely right. There is definitely some things that have to be thought about there. The other thing is that in this very simple process where I said, the one thing executes after another, we don't have any things where if it took, for example, multiple ticks of the clock to do the work, maybe a multiply takes 3 ticks of the clock, then if one instruction uses the result of the instruction preceding it, I still have to wait for the whole thing to finish beforehand, and I have to sort of stop the pipeline while the multiply finishes before I can get the result out to then maybe add 1 to it at the end. And those are called hazards, data hazards, and there is definitely some circuitry that has to look out for, well, I can't start the next instruction until the previous one has definitely finished, if it depends on it. And that also comes into play with our multiple robots over here. So we've actually managed to get to about early 2000s era now of CPUs. So this was the Sega Dreamcast, which was my favorite game console to work on, had an Hitachi SH4 processor that could do 2 things at once. And there were these rules about which 2 instructions the circuitry could detect didn't interfere with each other and thus could run together. And so you spent your entire time trying to write pairs of instructions that you knew would go together so that you got twice as many instructions getting through the pipeline each tick of the clock. And then we're going to increment the index, and incrementing the index moves it along to the next cell. Then we're going to say, well, add to the accumulator using our abacus.
So sometimes the way this is done by
well, again, in this instance, we're going to go to the